All right, so here's our bell ringer. This is the question here is asking, it's talking about light that's flashing, and they want to know what is the frequency of the light flashing in hertz. So if you haven't tried this on your own yet, strongly encourage you to do so. Again, this is recalling our equation from yesterday about frequency, how to calculate frequency. And if you forgot, the frequency is the number of events, and you can calculate the frequency of, like I said, pretty much anything that occurs periodically, divided by the time in seconds. It's very important in order for it to be in hertz, which is what they want here, right? Remember, hertz is inverse seconds, so you have to have seconds in there. So to find the answer is just 380 flashes divided by, you got to change 2 minutes into seconds. So off to the side, 2 times 60, because there's 60 seconds per minute, is 120 seconds. So you divide it, and you get around about 3.17 hertz. So this light is flashing about 3.17 times per second. Good deal. Okay, today we're going to be discussing a phenomenon called the Doppler effect. The Doppler effect happens with any kind of waves, but it can most easily be demonstrated with sound waves. So there are 2 videos here and a simulator I'll show you. For the video, I'm gonna stop the recording so you can watch that on your own, and you can do that now. Okay, so that video, again, what you heard was whenever you were outside the car, you get this characteristic where it goes up and then back down, and you get that sound, versus if you're in the car, the pitch didn't change. The horn stayed the exact same. So the frequency, remember with sound, frequency is what we hear. So the frequency changes, specifically frequency increases as it was coming towards us, and then it decreases as it goes past. You can also see this visually. Okay, so this is just a wave simulator. Let's go to the Doppler effect, which, there you go. Okay, so what they've got is, this is making waves, obviously, this is the source here, and then it's moving, right? So it's moving towards this right here, this is the observer. And here the speed of the source is fairly small. I can speed up in just a second. But what we see is, right, I guess I could show you this right here. This is the frequency. So this is like a little probe that's measuring frequency for us. So notice what happens as it comes towards us. The frequency is increasing. And as it goes past, so again, and then all of a sudden it gets much longer. The frequency gets longer afterwards, or a lower frequency. You can even see it visually here, right? I can speed up the simulation just a little bit. You can see it. And but again, if we look right here, it's apparent, right? The frequency is the number of waves per second. So the closer the waves are together, the higher it is. Here it's much higher. Here it's much lower. Oh, actually, no, that wasn't the one I wanted. Sorry. I did want that first one, but I wanted to change. Speed up a little bit. All right, let's look at it again. So I've exaggerated so you can see it better here, but it is very apparent that if you're measuring the frequency on this side, right, the frequency or the number of waves you see, they're clumped up together, it's much higher here than it is on this side. It's much lower. That's what the Doppler effect is. It's a shift in frequency. But why this is important is because the shift in frequency correlates to the velocity of, or the relative velocity between what we would call the emitter and the observer. Now, it doesn't matter which one's actually moving, right? In this case, it's the emitter, the thing that's making sound, is the one moving. But if the observer was moving, you would get the exact same thing. It's the relative speed between the two. In fact, actually, If they were both moving towards each other, that Doppler effect would be even greater, even have a greater exaggeration, so the pitch would continue to increase. The reason why this is important is because you probably have heard of something called Doppler Radar as an example. In Doppler Radar, they send out these ultrasonic sound waves. They bounce off of like big storms and big clouds, and they come back, and based on the shift in that frequency, they can tell which way the clouds are moving, if they're moving away or towards. This is also the same thing that gets used in police radar guns, right? So if you ever get pulled over for speeding, I know most of you aren't driving yet, but you'll be there soon. If you ever get pulled over for speeding, the reason what they're going to do, the reason why you can't argue your way out of the speeding ticket is because they just uses science. It just uses the Doppler effect. They send these ultrasonic frequencies get emitted from their radar. They bounce off your car and come back, and depending on that change in frequency that the machine reads, that corresponds to a velocity, and they can immediately tell your speed exactly how fast you were going. The equation for the Doppler effect is here. Now, obviously, you have this on the PowerPoint. It's up to you. I wrote it down because I think it's easiest just to see it, and I'm going to be using it in just a second. Well, you all are going to be using it as well. We're going to be using it together. So again, you see the key down here is telling you what is what, but FO stands for the observed frequency. FS is the source frequency. This is what's emitted. And you multiply, so it's really a ratio, if you can't tell, it's a ratio. And this little fraction here is going to be your, so V is the velocity of the wave. We're going to do sound today, and almost exclusively sound, and you don't have to write this down because it'll be on the equations or the problems, but sound is about 343 meters per second. So it's going to be the speed of the wave plus or minus the speed of the observer. So this is where it gets a little tricky because you use plus if the observer is moving towards the source. You use minus if the observer is moving away from the source. Most of the time, though, we're going to be dealing with the source moving itself. So a lot of times it'll just be this thing on top will be zero. Sorry, I should say VO will be zero because the observer may not be moving. In fact, usually I think in all the problems I gave you, the observer is still. They're not moving. So this top thing will just be really this plus zero. So it'll just be V divided by. And then now you've got the velocity of the source factors in here. Okay, so once again, it's still the velocity of the wave, which if it's sound is going to be 343 meters per second. But then you use plus if the source is moving away, and you use minus if the source is moving towards. The way I think about it is, you know those old silent films where the bad guy has like a really long mustache and a top hat, and he takes damsels and ties them to the railroad tracks. You're aware of this? So the way I think about it is I pretend I'm a damsel in distress on the railroad track. And if the train's moving away from me, that's a positive or a good thing. So if it's moving away, it's positive. If the train moves towards me, it's a negative thing or a bad thing. So if you think about yourself as a damsel in distress tied to railroad tracks, you won't forget which way to go. All right, I'll move on. Let's do our first example. Let me pull up my the copy I can write on. Oh, actually, well, it's fine. We'll just do this one. All right, I think here it says a NASCAR engine hums at 280 hertz. The car is driving towards you at 89.4 meters per second. Question number one, what pitch do you hear as the car approaches you? And question number two, what pitch do you hear as the car passes you? So we're gonna look at question number one first. Now, if you ever listen to NASCAR, you'll kind of know what I'm talking about here. I'm not a big fan of NASCAR, but my dad watched a lot of NASCAR, so I would hear it in the house. I don't get the appeal, but it is what it is. But definitely as the car moves past you, and they have the camera, especially ones like on the ground, you can hear this every time. You hear the same like wow 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 sound, right, where it goes up and then down as it passes. Okay, so I'll just do the first one. Car is driving towards you. Okay, so remember our equation here is going to be the frequency we observe is going to be the frequency of the source times velocity plus or minus the velocity of the observer divided by the velocity plus or minus the velocity of the source. Okay, now I don't have, well, I had it written down anyways. Let me double check my equations right. I had it written down, but I don't know what happened to it. Okay, observer's on top and source in the bottom. Okay. So, it's actually pretty easy. Like, really, these questions are hard. The hardest part will be the sign if you miss the sign. But otherwise, other than that, it's pretty straightforward. The observed frequency, that's what we're looking for. What do you hear? What pitch do you hear? That's going to be the observed frequency. Is going to be equal to the emitted frequency. We know this frequency of source is 280 hertz. Times. Remember, v is the velocity of the wave, which we know that this is sound. So sound has a speed in air of 343 meters per second. The observer is not moving at all. So this is just going to be 0. Okay. On the bottom is still v is 343, so 343. Okay, but here's where we got to make sure we're very careful. So the car is moving towards you. So remember, if you're a damsel in distress and this is a train moving towards you, it's a very bad thing. So it's going to be a minus sign for our sign there. And the velocity of the car is 89.4 meters per second. Okay, so we've done the hard part. The hard part's setting up, so we're pretty much done at this point. We just got to simplify an answer. So it's going to be 280 times, on top is 343. On the bottom is, oh, I found my equation, by the way, now. It was under my calculator. 343 minus 89.4. I get 253.6. Okay. Kind of running out of space, so I'm just gonna do the rest here, simplify and find my answer. I don't think anybody would miss it at this point. But I take 343 divided by 253.6, and I got like 1.35, and I'm gonna take that and multiply that by 280. So for our final answer, don't worry if we're off a little bit on decimal points. I get 378.7 hertz. About 379 hertz. Again, don't stress if we're off a little bit on the rounding. Okay, let's just do a sniff test here to see if, does that make sense, right? Because if the car is coming towards us, you may remember from the video we watched a minute ago, or that little demonstration on the simulator, if it's coming towards us, the frequency should increase. So if it's originally 280 hertz, and now I'm hearing 378.7 hertz, that matches at least my logical check there. So I think that's probably the correct. And I know, at the very least, I know I didn't mess up and use the wrong sign. So there's a way you can check on the sign, right? Because remember, if the thing making sound is coming towards you, the frequency should go up. As it passes you, the frequency should go down. Okay, so actually, hopefully you see that's pretty straightforward. It's not really that tough. It's really just making sure you have the right sign and then doing the calculator work. Okay, let's go ahead and figure out for what do you hear when the car passes you. So as you can probably tell, almost everything is the same except what's going to change. Well, if it's passing us, the thing that's going to change is this sign right here, right? Because the car is going to keep going the same speed, presumably. There's no information to tell us it's going to change. So then the only thing that's going to change is this sign. Instead of it being minus 89.4, it's going to be plus 89.4. So I'll write it out, but it's the exact same thing, right? It's 343. The observer is still not moving. whoops, 343 divided by, on bottom, 343 plus 89.4. And again, I'm not going to go through the details there because I think you'll be fine, and I don't want to take too much time, and I also just don't have a lot of space. But I'm doing the calculator work here. So I have 343 divided by, in parentheses, 343 plus 89.4. I got 0.793, so on. So multiply that by 280. And for my frequency, I got 222 point, we'll just call it 222.1 hertz. Again, does this make logical sense? As the car passes us, the frequency should drop. So if it was originally 280, now it's 222.1. Yeah, we got it. It works out. So then, as this car passes you, right, you're gonna hear this pitch change, right? It's gonna go from 280 and kind of almost, it'll drop through 200. Sorry, let me phrase that. It's gonna go from, as it's approaching 378.7. It's going to drop down through 280 all the way down to 222.1 in just pretty much a fraction of a second. And that's where you get that sound that you hear, right? You can hear that sound here. Actually, no, you can't, because that's not where the link is. Okay, hold on. You can hear that sound here. Hopefully it's not too loud. Okay, I'm ready. Okay, so again, that sound, that is that change from coming towards you to going away from you. That's the Doppler effect, at least for sound. Okay, cool. Let's try another one. Now this time, actually, let's skip that one and do this one. Okay, so what I would encourage you to do is go ahead and try this on your own. If you're watching the video, pause it here. And try this on your own, see if you can get the right answer, and then I'll come back and go over the correct answer with you all. Okay. Not rushing anybody. I'll give you a few more minutes, but there's the answer. I got And again, if we're off like a decimal place, it's not going to be a big deal. Should get about 197 hertz or 196.8 is what I got. But so again, if you got that wrong, there's two things I would double check on. Number one, biggest, most important, make sure you have the right sign. Because again, this is coming towards us. If we're damsel in distress on the railroad tracks, that's bad. So it's negative, minus 38. And then the second thing is just make sure you're putting in your calculator correctly. Or maybe just not trying to do everything at once, right? So take it in a couple steps. Because, again, if I just type into my calculator right now, 343 divided by 343 minus 38, I'll get the wrong answer. Because it does the order of operations first. You want it to subtract first. So if I was going to put this, if I was going to put like this part in my calculator, I'd have to type it in like this. 343 divided by parentheses 343 minus 38, close parentheses. And then I would do that times 175 and get my answer. Okay, let's look at one more. This time, let's try to solve for something else. Instead of just solving for the observed frequency, let's see if we can find, this is the speed, right? How fast, in which direction. So here it says tuber, it's his nickname, he's playing his tuba on the tube, the name of an underground train. He's playing a note with a frequency of 180 hertz. How fast and which direction would the train need to move in order for someone to hear a frequency of 280 hertz? So this time, this is different. We're looking for something different here. So let's see if we can just set up the problem with what we know and see if we what our unknown is. So I got to get my brush correctly set up again since it's on black background. Okay, here we go. The observed frequency, right? So I'm not going to write the equation. I assume you have it in front of you. You can see it. The observed frequency, we know, right? What do we want the observed frequency to be? We want it to be 280 hertz. How fast in order to hear 280? So 280 is going to be my observed frequency. It is equal to, we know the note he's playing has a frequency of 180 hertz. That's going to be our source frequency. Times. Again, speed of sound is 343. The top, right? The top is the observer. The observer's not moving. So just like it's been on all the other problems, it's just going to be 343 plus 0. Or minus 0 if you're so inclined. That's kind of like a half empty, half full thing. If you're an optimist, you add. If you're a pessimist, you subtract there, the 0. And then on the bottom, we have our, again, 343. That's the speed of the wave. But this time, let's think about this for a moment. If we want the pitch to increase, right, we want to go from 180 to 280, should this train be moving towards or away from us? Well, if we want the pitch to go up, it should be moving towards us. Remember, pitches go up as it moves towards. So if it's going towards us, that's a bad thing. Damsel in distress. Tuber's coming for us. So minus, I'm going to have a minus sign here. And then I don't know what the velocity is. The velocity of the source. That's what I don't know. So that's my unknown. So I've got everything set up. Now I'm just going to use algebra to get this thing by itself. Unfortunately, I have tons of room, but I would divide both sides by 180 first. Okay. So on the side here, 280 divided by 180. I get 1.5 repeating. Let's just call it 1.56. Equals, on this side, the 180s cancel. So now it's just 343 over 343 minus Vs. There's multiple ways you can go about solving this. Generally speaking, I always try to get if there's an unknown in the bottom, I try to get it to the top. So what I would do is I would multiply both sides by 343 minus Vs. And again, I'm unfortunately kind of out of room, so I'll write that off to the side, but I can't. So I'll just have to write it up here, I guess. So now, this is 1.56 times 343 minus Vs equals, on the other side they just cancel, right? I mean, I hope you can see that. I'm multiplying by this thing here, 343, whatever, so they cancel. So it's just 343. Okay, again, multiple ways you can do this. I would just divide by 1.56 probably. So divide both sides by 1.56, and again, you're dividing the whole thing, divide by 1.56. So 343 divided by 1.56. Okay, I have 343 minus Vs equals 219.9. And again, I'm going kind of fast here. I apologize, but I don't want to run out of time. And I also, this is on video, so you can always go back and look at it. Okay, so now, again, it's kind of tricky because I want to get Vs by itself. So I have a couple options. I could subtract 343 and then just divide by -1. I could add Vs to both sides and then subtract 219.9 on both sides. Either way you do it, you should end up getting 343 minus 219.9. To find our answer is going to be, okay, I'm just going to write it over here. For my final answer, I should get V is 123.1 meters per second. Which is very fast, unrealistically fast, honestly, but that's what we got. Now, this is the same calculation that a radar gun does, right? It does it almost instantaneously because it's built to do that. But if you have a police radar gun, it emits a frequency. That frequency is a known frequency. It knows what it emits. It emitted some frequency. That's going to bounce off, that bounces off this train, for example, And then let's say it bounces off and it said, okay, well, I emitted a frequency of 180, but now I notice the frequency is 280. What's going on? Well, it does that calculation real fast and finds that the train is moving 123.1 meters per second, which would be way fast and, of course, would result in a speeding ticket. There will be other applications for this Doppler effect that we will eventually get to. We're kind of building up to that once we get a good knowledge base, okay? All right, for good measure, let's look at one more where the observer's moving, and this will be our last one. Oh, sorry, wrong image. Oh, it is the right image. I just didn't mean for it to say bell ringer up there, but. Okay, like previous, I'm gonna give you a few minutes to try and do this on your own. Notice that, very important, there are two different velocities this time. The car is driving at a velocity, and presumably the car is driving towards Thomas, and Thomas is running towards the car. So again, this is the first one where the observer is going to have a velocity. So you may need to go back to your equation, look and see which way that's supposed to be, positive or negative, when you do this, okay? So take a minute, see if you can get this one, and then I'll come back and we'll look at the answer. Okay, here is the solution I have. Again, the thing that's different here is both observer and source are moving. So on top is the observer. If the observer is moving towards, it's positive. So I did 343 plus Thomas's 5 meters per second. On the bottom, again, if the car is moving towards him, it's negative. And it may seem weird that on one it's positive and one it's negative. That may be a little confusing, but hopefully, again, you look at your notes. So you have those. I had to reference my notes as well because I want to make sure I got it right. But it kind of does make sense in a way because they're actually both contributing, right? Because by him moving towards it, he's making the top bigger and the bottom smaller, so they get a bigger difference, right? So if he was moving really, really fast towards the source, then it would be an even bigger difference and an even greater shift in the parent frequency. But anyway, so on bottom, 343 minus 35, you do the math there, you should get 203.4 hertz for your final answer. Okay. So hopefully this makes sense. Again, the Doppler effect's really not too tough. You just kind of got to make sure you pay attention to those signs, be careful in the setup, and then, there's some algebra involved, varying degrees of algebra depending on what you're looking for. Okay. So hopefully that makes sense.